So hi everyone, I hope you hear and see me well. If you don't hear me or you don't see my screen, then please tell me on the chat. And if you hear me, please tell me too, cause yeah, it would be good if you hear me. We will be talking about solution to every problem of today's contest. I think first four problems were really easy, so we'll be talking about them only briefly, but we'll be talking about them. I see that you can hear me. So, yeah, let's start talking about the problems. First, we have problem A. And well, in problem A, we have like, in each test case, we are given a string of length 5. And then we want to say if there is more A's on or more B's in this string. So, well, it's just a problem to implement this statement, right? We will be iterating over our string and counting the number of every letter. So let me show you a code, because, well, there may be some beginners and they may want to see a code. But, well, it would be fast. We are reading our string and we are keeping those two counters, number of letters A, number of letters B, and then this is range for, I hope, many of you know it, and if not, you can write a for like this, and in X you will have, type of X will be always the type of variable stored in A. So here X will be char, cause string stores chars, right? And we are looking, if X is A, then we are increasing the number of A's, and otherwise we are increasing the number of B's, and then we are just counting. I hope that everyone understands this. I don't want to go into it any further, cause, well, it's really easy. So, oh, there is a question to zoom my code. Okay, I am zooming it. Give me a second. I will make my code bigger. Yeah, it's really small. I see this. So, a minute. Tell me if you see. Oh no, I have made my terminal bigger. That's not good. Do you see it now? Can you see it now? Okay, I hear that you can see my code. That's very nice. Okay. I have like 40 lines, so I can make it even bigger for you. Cause, well, it will be good for the future. Okay, let's stay like this, cause I think it's perfect. So let's go to problem B. In problem B we had, so problem B. So in problem B we had like a grid. Oh, here. And we had some, well, square or a triangle marked on this grid. And we know that, well, square, we all know how square looks, right? It's just a square on this grid. Or maybe it took, or maybe there's some, well, maybe there's some triangle, and we always knew that triangle looks like this, right? Its highest point, it's like it can't be reversed, right? Its base is like down, like yeah, we just know that with every other row the number of points in this row increases. So well, now we want to say if there's a triangle in this square, in this grid, or a square. So one simple observation is that the number of rows number of rows with at least one square marked, it's always greater than 1, right? Because, well, we know that the side of it needs to be greater than 1 because we have it in our statement. So now we can find the first row in which we have some marked square, the second row, and now we see that when we have a square, the number of when we have a square, the number of marked squares in like every row is the same. Here we have 3 marked squares, here we have another 3, and here we have another 3. But when we have a triangle, here we have 1, here we have 3, and here we have 5. So in every row there's a different number of squares. So what we'll be doing is just getting the counts of squares in every row and then checking if they are the same or not. That's all. So I will show you my code. I need this for a minute. Oh, wait. So let me show you my code. I hope everyone understands. But those are easy problems. I'm sorry that some of you may be bored, but well, we have to show them because maybe there are some beginners. So what I'm keeping the previous value, the value of previous row, and I'm keeping this variable is saying to me, well, have you already found the answer? So when the number of ones, here I'm finding the number of ones in this row, when the number of ones is greater than 0 and I haven't already found an answer, if the number of ones in the previous row is greater than 0, then well, I have found the answer. If we are the same, right, here it would be those two rows. If they are the same, then it's a square, and if they are different, then it's a triangle. And well, if the previous row is equal to 0, then, well, I am the first row. So I am just saying that the previous row is the number of ones in me. So I hope everyone understands. It's like, yeah, easy problem. So let's do the third problem. Problem C. Problem C. Okay. So in this problem we are given one number n, and we want to count the sum of the digits of all numbers from 1 to n. Right? So let's write some example. When n is equal to 12, then we have sum of 1 plus sum of 2 plus sum of 3 plus sum of 4 plus sum of 5 plus sum of 6 plus sum of... Let's say I will be counting the answer for 8 because I don't want to. For 6. Oh, because I don't want to. Then I know that, well, for those one digit numbers, well, the sum of digits in it is it, so it's not interesting test. So let's say sum of digits in 312, we know that it's just 3 plus 1 plus 2. So it's 6. So if you would like to count the... So yeah, the question, the problem just asks us to count the sum of the... It asks us to count the sum of s on some prefix of numbers, right, up to n. So, well, if we could find this sum of digits fastly, then we could just, before asking the queries, we could just pre-process all the answers, right? It would be just 1/4. I hope everyone understands this. If we could count this function fastly, then, well, we would be in home. We would know how to... We would just pre-process all the sums. So how to find the sum of digits of the number fastly? Well, we know that the last digit of our... We'll be adding the digits from last one to the first one. We know that last digit of number x is just x modulo 10. Right? That's just simple math. And we know to delete the last digit from our x, we just need to divide it by 10 with floor. This is deleting the last digit. Right? I hope everyone understands this, because, well, if we have 0 on the end, we'll just delete 0, and as we are dividing with floor, if we are we have something bigger than 0, then we are just first subtracting it and then deleting 0. That's just how dividing with floor works. So let me show you my code to this problem. Here I have implemented function getSum, which takes the number x and returns the sum of digits of x. So what I'm doing, I'm keeping the sum of digits, and then while x is greater than 0, I am adding the last digit and deleting last digit. And then I am pre-processing all the answers. If I know that I know the sum of s for I minus 1, then, well, I just need to add the next one. So if I know that if I know this sum from the interval 1 to 11, then to get interval 1 to 12, I just need to add s from 12, right? So, yeah, that's just it. And then when we are getting queried, we are just counting sum of n. So there is a question on chat. Hi Jan, should I try to solve problem by myself first that I did not solve? This the solution. Wait. Wait. Wait, I can see this, but if you are asking if you should... Yeah, I am going to debug. There is a question. If you are asking if oh, hey Jan, I should try to solve problem by myself first that I did not solve, then see solution, or just look at the tutorial? I think for me it depends on how long were you thinking about it. If you feel like you can't come up with anything else, then I think you should see the tutorial, and in the other case you should think about it more. There is question to explain C again, so one more time. We know that we can calculate the sum of digits of some number fastly, right? I showed you how to do this. Get the last digit with x modulo 10 and delete the last digit with dividing x by 10. So now what we will do is we'll pre-process the answer for all the queries before answering them. So how we'll do it? We know that if we have the answer for some query I, then to get the answer for some query I plus 1, we need to add the sum of I plus 1. Oh, and that's all. Yeah. I should probably wrote it down there. Wait, I will wrote it for you. But yeah, that's basically just all. So to get from I to I plus 1, we need to add s from I plus 1. So yeah, if you still don't understand, you can rewatch it, cause well, it's always saved, those videos. So let's go to problem D. Wait, I want to write it nicely. Yeah, okay. Let's go to problem D. So problem D. In problem D, we are given some array of numbers, and we want to divide those numbers into groups. And we are said that the every group must, in every group, okay, let me, okay, so, so like in problem D, we are, in problem D, we are given an array of numbers, and then we want to divide them into as less groups as we can. And we are said that the group is good if for every two numbers in this group, let's say we have in some group the numbers A and B, they must be different digit by digit. Every digit of them must be different. So let's say we are looking for every numbers in 31 binary digits, right? That's important. So let's say that we have some number 0, 0, 0, 1 and 1, 0, 1, 0. Then the group consisting of those two numbers isn't good, because as we see on the second digit, we see that the digits here are the same, right? But if we would change, let's say this 0, if we would change it to 1, then they would be good, because for every digit they are different. So now the observation in this task. Observation. Only pairs x negated are good. What does it mean? It means that when we have some number, let's say like this, then the observation is that for this number there is only one other number that's good, because we can just create it, right? We know that for this digit it has to be different, for this digit it has to be different. When we have 0 on some position, we know that in this other number we have to have 1 on this position. And if we have 1 on our position in x, then we need to have 0 in the other number. So now we see that all the groups are at most size 2, right? Because, well, group can only have size 1, or group can be consisted of A and negated A, right? So that's our only possibilities. So now what we'll do, first we are assuming that all the groups are of size 1, so every element of this array is in some different groups. And then we will be just creating those groups of size 2. So we will be iterating over every value of this array, and we will be just looking, oh, how many, let's say that we are on some value x. And let's say that we have that our count from x, so the number of x in this array is equal to 3. And let's say that count of x negated is equal to 2. Then we see that we can delete those two groups that we created before and just, make those group of x bigger, right? So how to implement this? We are keeping a map of those values. It could be an unordered map, but I used map. And when we are iterating over those keys, right? In map, when we'll be iterating over our map like this, in the first element we'll have the value, and in the second we'll have like how many elements. So now I am finding this negation, right? I'm finding not x. With the greedy I said to you before, I am always adding, if on some digit there is 0 on my value, then in negation there must be 1, and then if then I am just subtracting from the answer the minimum of those two values, right? It could be done easier, but I hope everyone understands this solution too. Right, because we see that our answer will just be the n minus number of groups with size 2, right? So what I am doing is just I am subtracting those groups of size 2. So what I am doing is just I am subtracting those groups of size 2. I see that I see that when I'm checking if, well, I can pair some of my negation with myself, that's all. There are questions, why haven't you used negative binary operating tilde? Well, I haven't used it because when you have unsigned ints, they have one more bit than we need. And when you have signed ints, then in signed ints, the first bit will be minus or plus. So let's say that we'll write the negation of, let's say, 4. What will be the negation of 4? It should be some big value but positive, right? But when you will check it, it's minus 5, and it shouldn't be. Because, well, that's just how negation works on signed ints. That's just how they thought of it. So let's go to another problem. But I hope everyone understands. Problem E. Now those harder problems with some... Well, those 3 problems could appear also on div2, I think. E could be probably B on div2, F could probably be C on div2, and G would probably be C on div2 too. So those are the harder problems. So if someone waited for this, that's good. So let's go to problem E. So in this problem E. problem E. So in this problem, we are said that we start with cards from 1 to n. So let's say we start from cards from 1 to 9. And then we are laying those cards down on the table. And how we are doing this? First, we are looking at all the cards that are odd, and we are just laying them down on the table in the order that they are in the deck. So we are putting 1, 3, 5, 7, 9. Then we are putting all the cards with all the cards that are divisible by 2, but they weren't all the cards that are divisible by 2. We are putting down all the cards that are divisible by 2 but not divisible by 4. So it will be 2 and 6. Because 4 is not twice the odd number. And then we are deleting them. Then we are putting all the numbers such that they are divisible by 4 but not 8. And then we are putting all the numbers that are divisible by 8 but not 16. And now, after all this putting, we want to say what is the k value on our table, right? And k can be big. So let's say here, if we would be asked k equal to 4, then our 4 value would be 7. So how to do this? For first, although I already simplified the statement, because here we see that they say that, well, we'll be laying down the cards that are 3 times an odd number. But if our card is 3 times an odd number, it's also an odd number. If our card is 6 times an odd number, it's 2 times some different odd number. So I say that we will only do those operations for a power of 2. And it's easy to prove. I will leave this proof to you. So how to implement something like this? So what I'm saying, we are first putting all the cards that are 2x plus 1. Then we are putting all the cards that are 4x plus 2. Then 8x plus 4. 16x plus 8. So how we will do it? If we'll go from the prefix to the suffix, right? Because first we'll put all those, then those, then those. So we will want to find the first such, I don't know, block of numbers. Let's call this block of numbers, such that the sum of all the blocks here, the number of numbers in all the blocks here, is greater than k, right? Because if it's smaller than k, we haven't added the required number of numbers yet. So how to count? So now what we want to do is just count the amount of numbers in one block, right? Because if we would know this, we would just go and find the first prefix, and then we know that, let's say, in this block we have 3 numbers, in this block we have 2 numbers, in this block we have 2 numbers. So if we know that our k is equal to 6, then we know that we want to find the first number in this block. How do we know this? We find the first prefix with sum greater or equal k, and then we know that in the last block we'll just find the number. Well, we already laid down 3 numbers here and 2 numbers here, so we subtracted 5 from k, right? Because we already laid down 5 cards. So from this block we want the first number. So how to count the number of numbers in some block? Well, we'll do it with simple dynamic programming. It can also be probably done easier, but it was most comfortable for me to do it with dynamic programming. If we would like to count the numbers in some suffix of blocks, so let's say we want to count the numbers in some suffix of blocks. So, well, the number in some suffix of blocks will be just all the numbers that are divisible by some power of 2, right? So then if I know the number of numbers in this suffix of blocks and in this suffix of blocks, then if I want to find this number of numbers in this block, then well, I can just subtract those two. Because I see that everything here will be counted in both of them, so by subtraction they all delete themselves, and this will be the only thing that's left. So how to implement it? Well, I'm keeping those counts in every of the 30 blocks, and then, as I said, the number of numbers in like the suffix of blocks is just the number of numbers that are divisible. We are just the number of number in some suffix of blocks is just the number of numbers divisible by 2 to the power of I. And then I'm doing what I said. When I know the number of numbers in like the next suffix, the suffix shorter by 1, then I can just subtract this to get, to get the exact number. And then, if k is greater than the number of elements in this block, then I am subtracting those numbers, right? I know that I want to find if I already put in like here those 4 red numbers, and I say that k is 5, then I can just subtract this 4 and find the first number on this suffix, right? It's just how it works. And then, well, if I know that I want to find the kth number in the if block, then I just have this formula that I wrote in here for you. All the numbers in kth block are of form 2 to the power of k plus 2 to the power of k minus 1. In the let's say if block, the numbers are of formula 2 to the power of e plus 2 to the power of I minus 1 times k. Okay. So I hope everyone understands. I'm sorry for such a speedrunning. Oh, and also how to get this formula? Well, we know that all numbers that are divisible by 2 to the power of a, but not divisible by 2 to the power of I plus 1, well, they just need to have the good rest when divided by 2 to the power of I plus 1. You can do the math by yourself. I think it's a good training to do the math by yourself. So let's go to problem G. Let's go to problem G, because, well, problem G was definitely easier than problem F. So problem G now. Also, there is question, can I take a help from GPT while stuck in any problem? So, I think ChatGPT is really bad at competitive programming, so I think if you are stuck at some problem, you should read the Codeforces tutorial or go to some Discord server and ask your question, like a Rictor server or this our server, community server. Yeah, I think that's what you should do. You should ask some people for help or read the tutorial. Okay. So let's go to problem G. Well, I will just say the math statement. So, statement in math more. So we are given a tree, and we are said that some of the vertices of this tree are red, and some of them are blue. And now we want to cut the minimal number of edges such that after cutting those edges, let's say we would cut those edge, this edge, this edge, this edge, and this edge. We want to, in every connected component of our tree after this, so our tree would look like this after those cutting. We'll have one vertex here. And also we'll have the big part of our tree here. That's how our tree. And let me give you the colors. Oh, also we will have something like this. So, well, when we have some vertices marked here, so we want to say what is the minimal number of edges we need to cut, such that after this cutting, if you look at those components, in one connected component there can only be, oh, and here we have something like this. In one connected component there can only be, there can't be both blue and red vertices, right? So if we would have like red vertex here, then this cutting won't be good. Because, well, in these connected components there is both blue and red edge. So let me go straight to the solution. We'll use dynamic programming. And we want to have dynamic programming like this. dp from v from 0, 1, 2. So we want to say minimal number of cuts. The minimal number of cuts such that v is in component 0, 1, 2 and everything is good. So what do I mean by this definition? Let's say that, of course, this minimal number of cuts in subtree of v, right? It's always how we are doing dp's over trees. So let's say that we have a subtree like this. Then, well, if we cut it, let's say like this, then we see that in the component of v is blue, right? So let's say that blue will be 0. That blue will be 1. If we cut like if we cut it like this, let's say we cut it here, then we see that in component of v is red, right? Because there is some red in this component, so we call it red component. So let's say that red is 2, because we have this state in our dp. And then the third option is that we cut those two edges, or those two edges. Then we see that in component of v there is neither blue or red. So let's call it white. White is 0. So now what are how to get some state? Well, I think it's really simple if you think about this. If I want to make I will be just looking at the sums of v, and then for every sum of v, I will be adding 1, so I will have to delete this edge to this sum or no. Maybe I will show you my code, because I think it's best to show this on code. So, if foo is white, then if foo is white, so if I am assuming that after cutting there will be neither blue or red vertices in foo, then when I am adding the value of my sun, then if my sun is either blue or red, then I need to cut this edge. And if it's white, then I don't need to cut this edge. And I'm doing the same logic for assuming that foo is blue and foo is red, right? I'm just thinking, when I'm doing this DP, I'm just thinking where I need to add 1 in this DP. In my DP, yeah. I need to add 1 where I need to cut this edge. That's the only case when I need to add 1. Right? So, I have foo. I have suns. And what I'm doing, for every sun, I am like deciding if I want it to be blue, if I want it to be red, or maybe I want it to be black. I will take the minimum of those 3 values, because, well, it's the best for me in my DP. I have counted already DP for blue, red, and black. So yeah, that's all. And also, when my when value in my vertex is blue, then I am saying that I'm sorry, I can only end up as 1. I can't end up as white or red. And the same, if I am red, I can only end up as I can't end up as white or red. So I am saying it's infinity. And then I'm just counting minimum of those 3 values. I am assuming that 1 is either white, blue, or red. So that's the solution. So now to problem F. I'm sorry if I'm speedrunning too much. If someone has a question, then please ask it. I sometimes just, So in this problem we have a grid. Let's go to problem F. I think it was solved by a really small amount of people. So that's really weird. It was from official participants, only 42 people solved it. So that's really weird. Yeah. But let me write it. So in this problem we are given a grid where we are given a grid. It is, let's say, square grid. It doesn't have to be 7. I will assume it's just, wait. Yeah. So we are given this grid, square grid. 2, 3, 4, 5. Okay, let me also write that. What we are doing now is problem F, yeah, toughest problem of this contest by far. It took me a long time, longer than I thought. And then some of the squares are marked black. So let me write an example test for you. When we have something like this, wait, I have to, oh, okay. Let me just write it. So now we are set. Now we want to delete some. Now we want to paint some of the black squares white, right? So we are deleting some black squares, painting them white, and after all the deletions, we doesn't want to have any those crosses, right? Here we have some cross, and here we have some cross, right? The cross is 5, it's like, I don't know, it's just a cross, it's just something like this on grid. It's just those 5 squares that are aligned in this shape. I don't know, it's just this. So now we want to say minimal number of black squares that we want to delete, such that there will be no crosses after this. So we see that in this example, it would be optimal. Let me copy this, because maybe I can. This would be really nice for me. Oh, I can copy this. Oh, but it didn't copy. Wait. That's not good, because I wanted to copy it to draw in the new version. Oh, it's copied. That's very nice. So, in this example, wait, the square that we would like to delete would just be let me draw it once again. In this test, the square that we would like to delete would be this square. Wait, let me... It would be this square. Because after deleting this square, we would get... Let me once again copy. Oh. Because after deleting this square, we would just have something like this. Oh, wait. Right? So no crosses here. We see that there are no crosses here. So now to the solution. Let's go from the... I will tell you some solutions, and then we'll just optimize it. So, okay. First, we can notice that if we delete some square, then it will delete some crosses, right? So for every square, we can calculate the set of crosses that it deletes. So we will of course enumerate every cross by its middle. So yeah, this is the middle, and we'll enumerate every cross by its middle. And okay, so we see that those squares here, they are only deleting this one. Those square here, let me draw it maybe once again. Yeah. Oh, that's bad looking. Well, let me make it better. Okay, nice. So, we see that for those red squares, the only crosses that it deletes, the only cross that it deletes is this cross here, right? For those blue squares, so let me write, this is the red square. For those blue squares, the only crosses that it deletes is this blue square. But then, there we have some red and blue square. It deletes red square and blue square, red cross and blue cross simultaneously, right? So now with sum 4 we calculated the set of crosses that every square deletes. So then we see that we can just say that every one of those sets is just a bit mask, right? So, well, how many bit masks do we have in like this simplest version? We have as many bit masks as there are squares. So there are 49 squares in max, so we have 2 to the power 49 bit masks. And we know that if we want to do this depend bit masks, right, we want to find the smallest subsequence such that its OR is equal to the full mask, right? So if we would have like 101, 1 and 1 0, 1 0 0 and 1 0, then we see that the smallest subsequence is those two, right? And we can do a simple DP on bit masks that I will show you later to calculate the smallest such subsequence. And we know that the complexity of this will be 2 to the power of length, right? Length of the mask is number of crosses, so 49, times number of squares, number of bit masks, so that's 49. So that's much too slow. But then we have our first observation. We see that, let me go lower. So there will be no cross that has its middle here, right? Because, well, we can't have a cross that is going out of our border. So yeah, we don't have like 49 possible crosses. We just have like 5 times 5, because here we have like 5 times 5. So we just have like 25. Maybe let me wrote it like better. 4. Okay. And then we don't have any crosses here. So we just have, as you see, 5 times 5. So now our complexity, we see that now we just have the length of, well, the number of masks is the same, but the length of every mask just got beaten down from 49 to 25, right? So now our complexity is 2 to the power of 25 times 49. It's still a little bit too much, I would say. But now for the other observation, and the most crucial. I think most people didn't have this observation. Let's draw our board. Let's draw our board. Let's draw it a little bit below. So we have like 3, 4, 5, 6, 7. So, let's say, yes, let's color our board like a chessboard. But I'm just coloring it like a chessboard. It's a really beautiful trick, I think, because we want to somehow lower this complexity. So, let's look on some cross. Do you see it? This cross, every cross, or this cross, or this cross, every cross appears only on the squares of one kind, right? So we can independently solve the problem for the black squares and white squares in this chessboard kind of thingy. So how many and also we have this thing that I showed you before. We have like the smaller triangles with the middles. So how many black squares do we have in it? Well, we have just 10 black square in it. 10? We have just 13 black squares in it. So that means that our complexity will be 2 to the power of 13 times 26, cause, well, times 24, or how many black poles do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 20, 21, 22, 23, times 25. And we will do the same thing for white squares, so times 2, right? So now our complexity is like really good. We can just implement it. So yeah, those are all the observation to these tasks. Now I will also show you this DP. It's really simple. Let's say that we have some masks and we want to find the smallest subset of masks such that their OR, so we know that, let's say, OR of this and like this is, OR means that the bit for the bit to appear in OR, for the bit to be set to 1 in OR, it must be 1 in at least one of the thingies. Yeah, of the masks. So, how to do this DP? We are calculating DP from mask. It means smallest subset such that we can get, it's really similar to knapsack, we can get mask. And when we are adding some mask to our DP, let's say we are adding mask X, then what we are doing is we will be just, well, let's say that we can get some mask like this in like with 3 numbers, with 2 numbers. And let's say that we are adding mask like this to it. Then, as we see, now it will be possible for us to get mask like this in 3 steps. So we'll be just pushing this DP. It's like DP with pushing. So how to implement this? DP. Well, when we have our DP, we are iterating over those previous masks that we want to push further. We have to iterate from the biggest masks to the smallest ones. Or do we have to? No, we don't have to. But I'm just iterating. And then I am saying that now it's possible for the OR of those 2 masks. K is the previous mask and mask from IJ is, well, mask from IJ is my X and mask and K is my mask state. And now I'm saying that it's now possible for OR of those 2 masks to be gotten in like this new way. DP from K plus 1. Right? So, I hope everyone understands. I'm really sorry if something was too fast, because I think there might be some things that I explained too fast, but, well, then you can watch it some other time, or join the community and ask the questions. I will be also answering your questions there. You have on the up of the chat, you have the link to our community. So now to the questions. Okay, First question is, maybe I will send this Discord link once again, because I see that they are some questions. This is link. And okay, where to find the Codeforces tutorial? Well, right now maybe there isn't Codeforces tutorial, because, well, they might post it only after the round. But normally the tutorial will be here, under the announcement. Then the other questions. In third question, why you have taken Lim plus 10? Well, that's just what I like to do. You could also... Let's go to the third problem. You could also just take Lim plus 1 here, because you know that. But I'm always taking Lim plus 10 for like safety. That's just one of the habits that I have. I think it's a safe habit. But it could also be Lim plus 1. Then I have a question about question D. If you want to ask it, you can ask it now, but yeah, if you are still here. And sir, is E tough? Well, I think E could be on some Div2 contest. I think it's around 140, I think. If I would be to judge it, I think it would be around maybe 1400. Yeah. So I don't know. For some people it will be tough, but for more experienced people it will be really easy. So it depends on which place are you in your competitive programming journey. So are there any questions? Because I will be happy to answer them. And if you, or maybe you can just ask them in our community. I think that would be great too. Also, maybe I could share this board with you. He asks me to judge. Okay, I will judge your solution to problem C. But maybe let's do it in private. My Discord, if someone is interested, it's Jotmyszka. So, or maybe wait, maybe I will delete it. If you want to ask some questions, go to this Discord. So, thank you for being here with me. Stay tuned, cause I think many big things are planned on this channel, and also there will be more solutions with me or some other really good people. And that's my profile if someone's interested. And also, see you next time, I guess. I hope that everyone liked it. So see you next time. And go to our DC, or go to Cheyenne's Discord server. And bye.